Principle 1. Manage using phased lifecycle. In this video, we are going to see about Principle 1. Manage using phased lifecycle. Create and maintain a lifecycle project plan. Importance of the project plan. How important is it to have a project plan? As far as to say that of all the unsuccessful projects of which they had knowledge, roughly 50% failed because of poor planning. The list of reasons for the failure of software projects looks like this: poor planning, ill-defined contract, unstable problem definition, inexperienced management, political pressures. Essentials of a software project plan. The essentials of a software project plan are given below. Project overview. A summary of the project that can be read by anyone, say a high-level manager, in a few minutes, and that will give them the essentials of the project. Phased milestone plan. A description of the products to be developed in each phase and of the associated development activities and schedules. Major products of each phase should be identified as discrete milestones in such a way that there can be no ambiguity about whether or not a milestone has been achieved. The component activities in each phase should be identified in some detail. A good example of a checklist of component activities is shown in the below figure. Project control plan. This plan indicates the project organization and associated responsibilities and how these may evolve throughout the project. A work breakdown structure identifying all project tasks to be separately controlled by job numbers. A resource management plan indicating how the expenditure of all critical resources, including such things as core memory and execution time, will be scheduled, monitored, and controlled, and a project and milestone review plan identifying the periodic and milestone reviews and all of the related essentials to perform the review, by whom, for whom, when, where, what, and how to prepare, perform, and follow up on the review. Product control plan. This plan identifies the major activities involved in software product or configuration, configuration identification, configuration control, configuration status accounting, and configuration verification, and how these activities evolve through the software lifecycle. Validation plan. This plan covers much more than the usual test plan and is discussed more in Principle 2. Operations and maintenance plan. This includes an overview of the concept of operation for the system and plans for training, installation, data entry, facility operation, output dissemination, and program and database maintenance, including associated computer facility, personnel, and support software requirements. Orient the plan around a phased development approach. The phased approach means that the major product of each phase must be thoroughly understood and preferably documented before going to the next one, as indicated in the waterfall as shown in the figure. When this is not done, the result is the costly variant shown in figure. In this case, problems are detected in later phases, that is, usually code and test, but frequently even during operations, which could have been detected easily in early phases and corrected inexpensively at that time. Correcting them in later phases means that a large inventory of design, code, documentation, training material, etc. must be reworked and retested, involving much greater expenses and delays in project schedules. The importance of good requirement specifications. The most important phase products in this regard are the system and software requirements because they are the hardest to fix up or resolve later. They are the easiest to delay or avoid doing thoroughly. Besides the cost to fix problems, there are other critical problems stemming from a lack of a good requirement specification. These includes top-down design is impossible for lack of a well-specified top. Testing is impossible because there is nothing to test against. The user is frozen out because there is no clear statement of what is being produced for him. Management is not in control as there is no clear statement of what the project team is producing. One very effective measure for detecting such insidious ambiguities is to check whether the requirements are testable as exemplified in the below table. Principle 2. Perform continuous validation. In this video, we are going to see about Principle 2. Perform continuous validation. There is one single message about developing reliable software which outweighs all the others. It is to get the errors out early. This is a major thrust of Principle 2, that is, perform continuous validation. Problem symptoms. One of the most prevalent and costly mistakes made on software projects today is to defer the activity of detecting and correcting software problems until late in the project, that is, in the test and validation phase after the code has been developed. There are two main reasons why this is a mistake. Most of the errors have already been made before coding begins. The later an error is detected and corrected, the more expensive it becomes. Based on result obtained both at TRW and at IBM illustrates the earlier point. Most errors in large software systems are in the early stages. On large-scale projects, and often on smaller ones, requirements and design errors outnumber coding errors. Problems such as interface inconsistencies, incomplete problem statements, ambiguous specifications, and inconsistent assumptions are the dominant ones. Coding problems such as computational accuracy, intra-routine control, and correct syntax still exist as error sources but are relatively less significant. Below table shows more detailed classification of the 24 error types encountered in the command and control software development project shown in figure. The predominant design errors tended to involve interface problems between the code and the database, the peripherals, I/O devices, and the system users. Increase in cost to fix or change software throughout the lifecycle. The more errors are made early, and one of the main reasons why software testing and maintenance cost so much. Couple that with the pressures to complete software projects within schedule and budget, and you can see one of the main reasons why software is delivered with so many errors in it. Thus, we can see that it's important both to get the errors out early and to make testing and validation more efficient. Getting errors out early. The first step is to incorporate early validation activities into lifecycle plan. Principle 2. Perform continuous validation counsels us to expand each phase of the software development process to include an explicit validation activity. The resulting elaboration of the waterfall chart is shown below. Each early validation subphase implies two things: the validation activity itself, a plan preceding it. Specific activities which aid in eliminating errors in the requirements and design phases includes the following: in-depth reviews, early user documentation, prototyping, simulations, automated aids. Principle 3. Maintain disciplined product control. In this video, we are going to see about Principle 3. Maintain disciplined product control. The need for product control. The waterfall chart shown in Principle 2 is actually an oversimplified model of the software development process, even considering the refinements discussed under Principle 1. In fact, any good-sized project must accommodate changes in requirements throughout the development cycle. Many occur because of changes in the external environment. New government reporting regulations, improvements in technology, user organizational changes, changes in the overall system aircraft, bank, refinery, retail store of which the software and information system is a part. As these changes impact the system development, it is very easy for different versions of the documentation and the code to proliferate. Then, when testers or users find that the actual system is different than the one they have been preparing for, it can often take a good deal of time, money, personal strain, and sometimes legal action to straighten things out. Thus, it is most important to maintain a disciplined product control activity throughout the system lifecycle to avoid such mismatches. Baseline configuration management. The most effective system of software product control that we have found is at baseline configuration management. A baseline is a document or program which undergoes a formal validation or approval process and thereafter may only be modified by formal procedures established by the project. Before being baselined, a document such as a preliminary design specification for a software subsystem is easy to modify. After undergoing a preliminary design review, the document is baselined and enters into formal configuration management, under which any proposed changes must be approved by representatives of all parties concerned and audit trails kept of all change activities. The interrelationship between the system phases and the major system reviews and audits during the software lifecycle. Detailed system lifecycle model for baseline configuration management. The process of product control with respect to these established baselines is termed configuration management. It consists of 4 basic functions: configuration identification, configuration control, configuration status accounting, verification. Configuration identification. The configuration of a computer program is identified by and documented in a series of specifications, some of which identify its required configuration and others are achieved configuration. Configuration control. In the configuration control process, changes to the established specifications of a computer program and to the program itself are classified, evaluated, approved or disapproved, released, implemented, and verified. Configuration status accounting. Configuration status accounting is the recording and reporting of data concerning a computer program's configuration identification, proposed changes to its configuration identification, and the implementation status of approved changes. Verification. A series of configuration reviews and audits provide verification that the performance achieved by the product is the performance required by the development specification and that the configuration of the product is accurately specified in the product specification. On large projects, there may be quite a few baseline documents including such items as interface specifications and data requirement specifications, and the configuration management system is quite formal. Principle 4. Use modern programming practice, that is MPP. In this video, we are going to see about Principle 4, Use Modern Programming Practices, that is MPP. The use of modern programming practices, that is MPP, including top-down structured programming, that is TDSP, and other practices such as information hiding, helps to get a good deal more visibility into the software development process, contributes greatly to getting errors out early, produces much more understandable and maintainable code, and makes many other software jobs easier like integration and testing. However, MPPs are by no means a substitute for the other basic principles, as some projects have proven. These are projects which started using MPP but got out of control through deficiencies in planning, project control, or validated requirements and were not even brought to completion. Result to date. There have been quite a number of papers written which cite impressive productivity gains due to the adoption of modern programming practices. Even more than with the other factors, it has been difficult to distinguish the gains due to MPP from the effects of possibly correlated factors. Use of better people, better software tools, higher management visibility, concurrent improvements in management, etc. The below table shows the results from a workshop in which a reasonably thorough but far from exhaustive attempt was made to relate several sets of collected data within a consistent framework. Early experiences with MPP average. The negative impact of MC Auto 73 was due to inadequate preparation and misuse of some of the MPP. Subsequently, a more expensive analysis of the IBM database was performed. Their productivity ranges represents the ranges between projects using an MPP 66% of the time and projects using an MPP 33% of the time. Structured programming 1.78, design and code inspections 1.54, top-down development 1.64, chief programmer teams 1.86. The larger productivity range for use of chief programmer teams may also be due to another correlation effect. Chief programmer teams tend to be more frequently on smaller projects than on larger projects, and smaller projects were the more productive in IBM sample. Principle 5. Maintain clear accountability for results. In this video, we are going to see about Principle 5, Maintain clear accountability for results. Even if you follow principles 1 to 4, there are still ways your project can run into trouble. These data came from percent complete estimates given in weekly progress reports on a project several years ago. A manager receiving such estimate has somewhat the feeling of having sent the programmer into a deep, dark tunnel into which he has no visibility. From time to time, the programmer can be heard saying, "I'm 90% through" or "I'm 98% through," but it's often a long time before he finally emerges. The main problem here is insufficient concern with Principle 5, maintain clear accountability for results. Each individual on the project team should have a clear statement of the results for which he or his group are accountable, and a clear understanding that his future rewards depend on how well he does in producing those results. For a project to be able to do this, one additional thing is needed: adequate visibility into each person's or group's project performance. This visibility is particularly difficult to achieve on software projects with their lack of tangible products. To get this visibility, it is necessary to break the software process down into a large number of well-defined steps and to organize the project around these steps in such a way that each individual can tell whether he is doing his job well or not. Macro-scale accountability. On a macro scale within the project, these steps are the major milestones. Thus, project managers and assistant project managers have clearly established objectives and associated schedules and budgets. Their project plans include a statement of their operating assumptions about interfaces, government-furnished equipment, key personnel, computer availability, and any other factors which will influence how will they do their job. These statements, of course, imply accountability items for other project personnel. Intermediate scale accountability. On an intermediate scale, accountability mechanisms include not only milestones but also formal agreements between subgroups. One such is a written project work authorization between the project organization and the performing organization, identifying the specific sub-project deliverables to be produced and their associated schedules and budgets. Thus, on TRW projects, the independent test team will not accept a module for test until it has passed the following objective tests: satisfactorily exercised every program, branch, and every executable statement. Satisfactorily passed a functional capabilities list test based on a list prepared from the design spec by the independent test team. Demonstrated conformance to all project programming standards by passing through a standards checking program, the code auditor to be described below. Closure of the problem report is handled by another special form which must be reviewed and signed off by the independent test team. Principle 6. Use better and fewer people. In this video, we are going to see about Principle 6. Use better and fewer people. Let's suppose that you conscientiously follow Principles 1 to 5 above. Will this guarantee you a successful project? Not necessarily. Avoiding such a pitfall is a subject of Principle 6. Use better and fewer people. Variability among personnel. One main motivation for Principle 6 is the wide range of variability among individuals with respect to their software productivity. In one controlled experiment, it was found a variation of up to 26:1 in the time required to complete a programming assignment. Another experiment at TRW found a variation among individuals of 10:1 in the number of errors remaining in a complete program. IBM's analysis of structured programming productivity have shown a typical variation of 5:1 among individuals. Interpersonal communications overhead. Another main motivation for Principle 6 is that of reducing the communications overhead on a project by getting the job done with fewer and more productive performers. As indicated before, a group of n performers has a potential of n into n-1 by 2 communication paths to be concerned about. On larger projects, a hierarchical project organization will reduce this number, but the effect is still considerable. How fast the communications overhead grows when each individual spends 5% of his time in sideways communication with each member of his group and 15% of his time in upwards communication with his supervisor, assuming an average group size of 4 at each hierarchical level. Even with a 10% task, the communications overhead, the difference between the upper curve of potential productivity and the lower curve of the actual productivity has grown to 37%. Applications of Principle 6. Here are some particular high leverage applications of Principle 6. Don't try to solve project schedule problems by adding more people. You will just be adding more communications overhead, particularly as the new people try to learn what's going on. Don't load up a project with a lot of people in the early stages. This is the period during which communications are most intense and the requirement and design are most volatile. Getting a lot of people into the act at this time just means getting a lot of wasted effort. Set up career paths, salary scales, and other benefits to reward high performers commensurately. As seen above, top performers typically do 5 times as much work as the bottom performers, but they are never paid anywhere near 5 times as much. Going in this direction will increase your average cost per performer, but decrease your average cost per instruction even more. Pays out the bottom performers. This is never a pleasant thing to do, but with enough planning, time, and sensitivity, it can be done in a humane way with no embarrassment and more secure and satisfying alternate job for the employee and a healthier situation for all concerned. Principle 7. Maintain a commitment to improve the process. In this video, we are going to see about Principle 7. Maintain a commitment to improve the process. Principles 1 to 6 are not quite enough to guarantee a healthy software engineering organization. They are enough to get an organization to do good 1982 vintage software engineering, but not enough to ensure that the organization keeps up with the time. Further, there needs to be a way to verify that the particular form of the principles adopted by an organization is indeed the best match for its particular needs and priorities. This is the motivation for Principle 7, maintain a commitment to improve the process. This commitment is not large in terms of dollars, but it is significant in terms of the needs for planning and understanding your organization. It implies not only that you commit to trying new software techniques that look promising, but also that you commit to set up some plan and activity for evaluating the effect of using the new techniques. This in turn implies that you have a way of collecting and analyzing data on how your software performs with and without the new techniques. Data collection and analysis. Such data collection can be expensive, but it does not have to be. In fact, it is most effective when it is done as a part of the process of managing software projects. The need for visibility and accountability expressed in Principle 5 requires that projects collect data on how their schedules and resource expenditures match up with their project plans. The below table shows the type of information on software errors that can be gleaned from problem reports. Sample error category list. We have been able to use such data to determine priorities on developing cost-effective tools and techniques for improving the software process. Maintaining perspective. Another reason for Principle 7 is to make sure that the principles serve as a stimulus to think about how best to do your project, not as a substitute for thinking about it. As long as software engineering involves people, there will be no way of reducing everything to a book of principles and procedures. Another way of putting the above is, if the principles conflict with common sense, use common sense and iterate the principles. For example, Principle 6 says, use better and fewer people. If you take this too literally, you would use a top-flight programmer to serve as your program librarian on a chief programmer team. But this has already been shown to lead the problems. Thus, an iteration of Principle 6 would certainly include, as an added interpretation or guideline, match the right people to the right jobs. Features of good software. In this video, we are going to see about features of good software. While developing any kind of software product, the first question in any developer's mind is, what are the qualities that good software should have? Well, before going into technical characteristics, it is necessary to state the obvious expectations one has from any software. First and foremost, a software product must meet all the requirements of the customer or end user. Also, the cost of developing and maintaining the software should be low. The development of software should be completed in the specified time frame. Well, these are the obvious things which are expected from any project, and software development is a project in itself. The three features of good application software are software quality triangle with feature, operational feature, transition feature, revision feature, operational feature. These are functionality-based factors and related to exterior quality of software. Various operational features of software are correctness, usability or learnability, integrity, reliability, efficiency, security, safety, correctness. The software which we are making should meet all the specifications stated by the customer. usability or learnability. The amount of efforts or time required to learn how to use the software should be less. This makes the software user-friendly even for IT illiterate people. Integrity. Just like medicines have side effects, in the same way, a software may have a side effect, that is, it may affect the working of another application. But quality software should not have side effects. Reliability. The software product should not have any defects. Not only this, it should not fail while execution. Efficiency. This relates to the way software uses the available resources. The software should make effective use of the strong space execute command as per desired timing requirements. With the increase in security threats nowadays, their factor is getting importance. The software should not have ill effects on data or hardware. Proper measures should be taken to keep the data secure from external threats. Safety. The software should not be hazardous to the environment or life. Transition feature. Importance of any of these factors varies from application to application. Interoperability, reusability, portability. Interoperability. Interoperability is the ability of software to exchange information with other applications and make use of information transparently. Reusability. If we are able to use a software code with some modifications for different purpose, then we call software to be reusable. Portability. The ability of software to perform same functions across all environments and platforms demonstrate its portability. Revision feature. These engineering-based factors related to interior quality of the software like efficiency, documentation, and structure. These factors should be inbuilt in any good software. Various revision characteristics of software are maintainability, flexibility, extensibility, scalability, testability, modularity, maintainability. Maintenance of the software should be easy for any kind of user. Flexibility. Changes in the software should be easy to make. Scalability. It should be very easy to upgrade it for more work or for more number of users. Testability. Testing the software should be easy. Modularity. Any software is said to be made of units and modules which are independent of each other. These modules are then integrated to make the final software. Quality requirement in different application areas. In this video, we are going to see about quality requirement in different application areas. Some industry analysis would argue that the software crisis was and often exists due to the lack of discipline of the programmers. A software or website that calculates wrong results is defective, as also the one that fails to handle the expected speed or volume of business operation. One may keep probing, but the fact remains that the utility of a software or system could not be realized according to its expectation. Problems can be attributing to a weakness in planning, design, usage, people, and many more factors. Ultimately, the question that arises is, who suffers when the software behaves below expectation of the developer, implementer, buyer, or the user? The question is, what are the key factors that should be considered to avoid a project from becoming chaotic? The answer is not a single dimensional. Multiple parameters are required to be focused on a management and control of the multi-layers of software complexity, with each layer being affected by multi-factors and multiple criteria. Summarizes various dimensions that can be measured and analyzed to study software quality. Multiple layers of software quality indicators. Detailed frames of software characteristics. Multiple layers of software quality indicators. Software utility is a core external measure that defines software quality from supply as well as demand point of view. The supplier's view of utility should express the gain achieved from the effort expended in various activities of the product development cycle, such as research, design, and development of a particular software project or product. The customer's view of utility should express the usefulness and usability of a product. The usefulness implies the benefits accrued by developing a software product, while usability implies the ease with which the deployment can happen. The producer's and customer's utility is obtained through the achievement of quality of the product, process, and environment. The product quality defines all the attributes that can be measured or experienced while using or seeing the product. In case of software accuracy, reliability, and ease of use, etc., are the attributes of product quality. One can compare one product with another by comparing the transaction cycle or number of concurrent sessions supported by the product. Process quality indicates the capability of a process to produce a quality product with optimal use of resources. Organizations define processes, baseline, and standards to ensure that different workers carrying out similar process have a consistent way of working and also meet the minimum performance standard. The quality of the process in turn depends on many factors such as the quality of planning, design, production, verification, testing, and use. An organization weak in systems planning may overlook one or more factors, thus making a process definition weak in itself. For example, a project manager may define a written approval from his desk as a mandatory qualifier before beginning a code modification. Process quality is difficult to obtain if the internal organizational environment does not support process standardization and quality culture. Adequate tools for automation and measurement, proper user training, management commitment, and quality of solution providers are some of the factors that define the quality of environment. Achieving quality is inherently strenuous due to the difficulty in finding the best mix of many such, sometimes contradicting priorities.